Hello everyone, welcome to my presentation. My name is Jiayu. My major is mechanical engineering. The research direction of our team is tungsten carbide metric composite. Now I'll give a presentation on our recent research results. The name is Preparation of High Performance Tungsten Carbide and Magnesium Oxide Composites by Spark Plasma Sintering. The first part is research status of blendless cemented carbide matrix composites. Cemented carbide is a kind of alloy material mainly made of carbide of refractory metals such as tungsten carbide and titanium carbide and bonding metals such as cobalt and nickel by powder metallurgy process. Cemented carbide has the advantages of superior hardness, significant corrosion resistance, and abrasion resistance. Thus, it has been widely used in mechanical manufacturing, aerospace, oil draining, milling dies, and cutting tools. The rich tungsten resources provide an important resource guarantee for the development of the world cemented carbide industry. But looking around the world, cobalt is an important strategic resource. The price of cobalt is expensive and continues to rise, which is very unfavorable to the sustainable development of the cemented carbide industry. And the cobalt element is harmful to human health, and its chemical property is active, so it's easy to corrode. In order to solve these problems, tungsten carbide without a metallic bond face was fabricated. Researchers added metallic carbides or metallic oxides such as titanium carbide, aluminum oxide, or magnesium oxide to tungsten carbide matrix to improve its performance. It has been seen from this figure that scholars have gradually carried out research on substitute cobalt in recent years, mainly focusing on intermetallic compounds such as nickel, aluminum, iron aluminum, and oxides such as aluminum oxide and magnesium oxide. Such research has been carried out around their mechanical properties and engineering applications such as cutting tools. For the preparation methods of composite materials, there are several main sintering processes as follows. Different sintering processes have different advantages and disadvantages as well as applicable materials, but to a certain extent, they can improve the density of sintered blocks, inhibit grain growth, and improve material properties. SPS is a superior technique for materials that are hard to sinter, such as ceramics, hard metals, metal matrix. Based on the above research status, we have carried out the following research: novel tungsten carbide matrix composite without bonding phase. Commercial powders of tungsten and magnesium were used as the raw materials in order to break the agglomerators and refine the size of composite. The powders with tungsten and magnesium were placed in bone meal to mix as shown in Figure 1. Based on our previous work, the mass rate of tungsten carbide to magnesium oxide of 19.6 and 4 was adopted. According to the mass rate of 10 and 1, the powders and cemented carbide milling balls were put into the container and mixed for 50 hours and 350 revolutions per minute in vacuum. Next, tungsten carbide and magnesium oxide composites are called as WM composites for short. SPS was used to prepare the compact WM composite with high vacuum conditions in the temperature range of 1100 degree to 1400 degree and the pressure ranging from 30 to 50 megapascal. Figure 3 was the pattern of the as-milled WM composites powders from Figure 3A and Figure 3B. WM composites powders ranging in size from 0.1 to 1 mostly showed irregular polygonal shapes and good surface integrity. It indicated that the tungsten carbide particles and magnesium oxide particles were obviously refined after 50 hours of ball milling. To further confirm the distribution of tungsten carbide and magnesium oxide in the WM composites powder, BSE and EDS was adopted. As shown in Figure 3C, the bright faces were tungsten carbide particles, and the gray face was magnesium oxide particles, correspond to the results of EDS in Figure 3D. Figure 3E displays the specific distribution of 4 elements, tungsten, carbide, magnesium, and oxide in WM composites powder. On one hand, the magnesium oxide particles were reduced to the nanoscale after ball milling, ranging from 100 to 300 nanometers. On the other hand, the nanoscale magnesium oxide particles were evenly dispersed during the matrix. Figure 3F showed the mass fraction and atomic percentage of 4 elements. It can be seen that magnesium and oxide content were constant with the experimental values. In addition, the mass fraction of oxide showed that the powders were not oxygened during the vacuum ball milling process. Figure 4 showed the X-ray diffraction dramas of A to D sintered WM composites with different sintering temperature. According to Figure 4, tungsten carbide and magnesium oxide and subcarbide tungsten carbide were detected in all samples. There was no peak of impurity phase, indicating that no significant reaction occurred between the tungsten carbide and magnesium oxide during SPS. It was observed that tungsten carbide is the dominantly phase from all the XRD diffractions. Meanwhile, it can be found that the amount of the D-tungsten carbide phase in WM composites increase with the exceed of temperature. The occurrence of the D-tungsten carbide phase is mainly due to same decomposition and oxidative diffraction and at high temperature by the following equation. Figure 5 displayed typical microsculpture for WM composites centered at 1100 degree, 1200 degree, 1300 degree, and 1400 degree with corresponding average tungsten carbide grain size. According to the tungsten carbide grain size distribution in the lower right corner, conforming the mostly fraction of grains were between 1 and 4 UM. The results showed that the size of tungsten carbide particles in sintered samples was constant with that of the initial tungsten carbide powders, indicating that the growth of tungsten carbide particles was inhibited during consolidation. This information of the fine grains may be related to the SPS process. Compared with traditional sintering methods, SPS process promotes sintering of powder particles through common usual electric discharge and spark plasmatism. Meanwhile, the applied extra pressure helps strengthen consolidation while limiting grain growth. Figure 6 displays the hardness, fracture strength, and the fracture toughness of the WM composites and the different sintering temperature. From Figure 6a, the viscous hardness had slightly decreased from 1,685 HV to 1,616 HV, when the sintering temperature increased from 1,000 degree to 1,200 degree. As the sintering temperature rose to 1,400 degree, the hardness increased dramatically from 1,616 to 1,700. It has shown that the viscous hardness state shows the same law with grain size. Conversely, the fracture strength increased from 1,008 to 1,348 firstly, and then decreased from to 1,032 observably. The highest value of fracture strength was achieved when the sintering temperature reaches 1,200 degree. Fracture strength relied on hardness and fracture toughness when the pros were eager and microstructure had a major impact. As described in Figure 6c, the fracture toughness of WM composites increased with the increasing of sintering temperature. Remarkable, the fracture toughness of WM composites was not decreased with increasing viscous hardness, which is inconsistent with the fracture toughness of conventional blendless tungsten carbide composites and cemented carbide. An important reason for the fracture toughness increasing was that high fracture toughness corresponds to high density. Higher relative density will lead to less pores and better interfacial bonding. Therefore, the strength of the tungsten carbide and tungsten carbide interface bonded without the blender face was important to withstand the stress required for deformation. The specific reason for the sustained increase will be investigated by the microstructure of fracture. Next, WM composites centered at 1,200 degree were further characterized to investigate the mechanism of reinforcement and toughening. The SEM imaging of WM composite and EDS mapping were demonstrated in Figure 7. The results showed that the mass fraction of tungsten carbide and magnesium oxide in the composites were basically the same as the amount added during the preparation, and nearly no impurity was produced during the ball milling and SPS process. Thus, the ball milling and SPS process in this work help facilitate the dispersion of magnesium oxide. The finer microsculpture, especially the narrow-sized magnesium oxide, distributed along the tungsten carbide grain sets in the WM composite, plays an important role in obtaining high fracture strength. And the SEM image of the fracture surface of the WM composite was shown in Figure 8. From the observation of the fracture surface, the fracture mode of WM composite is mainly a mixture of transgranular fracture and intergranular fracture. Hybrid fracture models may be caused by local residual stress caused by thermal expansion. In general, the occurrence of the fracture mode was also associated with interface bonding stress, since cracks tend to propagate along weaker interface. Meanwhile, the occurrence of a transgranular fracture in WM composites was also attributed to the uniform distribution of magnesium oxide that enhanced the interfacial bonding. The progression path of indentation tracks in WM composites was shown in Figure 9. Since fracture toughness is related to crack growth resistance, crack growth path analysis is a valid way to discuss the track growth mechanism. The track bridging and the track deflection in the track progression path can be found in WM composite in Figure 9b. When the crack encounters magnesium oxide, the obstruction effect of magnesium oxide will change the direction of crack progression path. The deflection has been reported to mainly depend on the particle microsculpture and the percentage of the reinforcing phase. It has been seen from the Figure 9 that magnesium oxide are disparate in the tungsten carbide matrix. When the crack propagates near the edge of magnesium oxide, the crack will deflect and propagate in a zigzag path, leading to the dissipation of fracture energy. If the crack progresses around the magnesium oxide center, crack bridging will be occurred. The increased cracking bridge is a more effective mechanism for promoting toughness. WM powders were synthesized by hand engineering planetary ball milling method. According to the experimental results, the following conclusions can be concluded about the WM composites. Thank you very much.